Hello everyone. We will have a new session today, safe decontamination and advanced recycling of plastic medical waste. Biomedical polymeric metrology and sustainable process engineering, we will make this step high density medical polypropylene, polyethylene, and polyvinyl chloride. So we have the target for that. The healthcare sector rely heavily on single-use plastic polymer due to their exponential sterility, durability, biocompatibility, and low production cost. Syringe, intravenous IV fluid bag, that gets catheter and personal protective equipment are primary compounds of high-grade polypropylene, polyethylene, polyvinyl chloride, and polyethylene terephthalate. Globally, hospitals generate thousands of tons of these plastic waste streams daily. Historically, up to 80% of this material has been treated as infectious biohazard waste, resulting in direct mass incineration or disposal in deep in landfill. Traditional incineration destroys the material value and creates environmental concern regarding the emission of chlorinated dioxins, furans, and heavy metal ash. Transitioning to a circular economy requires a safe multi-para framework that combines absolute biological sterilization with cutting-edge mechanical and chemical recycle techniques. This allows hospitals to safely reprocess contaminated plastic into high-purity industrial polymers or chemical feedstock while maintaining a zero infection standard. Before any recycling process can occur, plastic medical waste must achieve a very long reduction to eliminate blood-borne pathogens and virus. Decontamination must be achieved without altering the polymer's structure, high integrity, or creating toxic high products. Modern closed-loop recycling networks use automated trending integrating autoclave under high vacuum heavy machine plate through the medical plastic into small uniform flake. This shielding ensure complete heat penetration and break the visual identity of needle and syringe. High pressure saturated steam and then introduced. Low temperature electromagnetic microwave disinfection. To process heat sensitive polymers that soften or degrade during standard steam treatment facility to deploy microwave disinfection ensured plastic are moistened with water misty and exposed to high frequency electromagnetic field. These microwave energy rapidly vibrate water molecules with solar pathogen, destroying cell walls via localized dielectric friction. This process operates at lower temperatures, saving energy and preserve the polymer chain length of the plastic for mechanical extrusion. Once sterile, mixed medical plastic must be stored into pure single polymer fraction. Mixed plastics cannot be co-extruded to thermodynamic which cause structure cracking in recycled matter. Near-infrared optical sorting sterilized flake pass long high-speed conveyor belt beneath sensors. The unique infrared reflector signature of each polymer is identified by an AI-driven classification algorithm with millisecond trigger presses compressed air jets to sort through the flake into distinct collection pins with over 80 and 98% purity. Supercritical fluid density is separation utilizing specialized fluid chambers where water or carbon dioxide is modified path is a critical point allow for precise density tuning. This method separates volume molifying from dense fluoropolymers and BVD based on minor difference in physical appearance, avoiding the use of toxic chemical solvents. Chemical recycling and depolymerization innovation. Mechanical recycling eventually shortens polymer chains, limiting the material to 3-4 life cycle before it degrades. Chemical recycling overcomes the limitation by breaking down plastic waste into its primary chemical building blocks, which can be repolymerized into pristine virgin-grade medical plastic. Control the catalytic pyrolysis sterilized medical polyolefin are fed into an oxygen-free thermochemical reactor and heated alongside zeolitic catalyst to crack complex carbon-hydrogen bond. The resulting hybrid pyrolysis oil match fossil-derived crude method. It can be fed directly into standard petrochemical cracker to produce new virgin-grade ethylene and propylene monomer, enabling true closed-loop recycle for medical application. Multi-layered medical plastics such as plaster pack or a composite tube can't be mechanically separated. Supercritical solvents use green solvent like water or ethanol heated past their thermodynamic critical threshold. In this state, the fluid selectivity breaks specific ester or amino bond within complex polymers like polyurethane, dissolving individual layers and allowing for the clean recovery of aluminum foil and raw chemical monomers. Technical performance and validation matrix. So target polymer stream, decontamination and processing method, resulting reclaimed product, primary application and verification, high-grade polypropylene, integrated through autoclave followed by mechanical granulation and clean extrusion, high-pure secondary pulp, industrial storage, battery casing, and non-clinical automotive components. Continuous microwave disinfection followed by zero catalytic pyrolysis, virgin equivalent pyrolysis, petrochemical feedstock for manufacturing grade medical bag. Two-stage catalytic dechlorination and chemical solvent extraction, pure plasticized oil and neutralized chlorine salt, industrial flow helix, flexible cable sheeting, and architecture conduit. Supercritical flow solvents used is an alcohol solvent separate pure aluminum foil and a clean organic monomer, repolymerize plastic and raw metal, manufacture feedstock. Material redesign, the future of medical bioplastic. The ultimate innovation frontier shifts the focus from waste processing to smart product design. Up to 40% of the story sorting challenges in medical recycling stem from complex multi-polymer assembly. Biomedical engineering companies are developing medical grade composable biopolymers such as polyhydroxyalkylate and high-crystallinity polylactic acid, formulating derived from renewable agriculture sugars. This bioplastic matches the strict structure and safety standard of traditional polymer in clinical trials. One processes through automated non-incision autoclave. This bioplastic can be safely composed in industrial anaerobic digester or chemical recycling to raw carbon stream. This material evolution eliminates long-term microplastic waste, reduce rinse on fossil resources, and build a sustainable closed-loop life cycle or recycled material.